So we have seen this k-means clustering algorithm, and a big problem in it is the choice of k. So hypothetically, we could come up with some kind of a cross-validation for the choice of k, but in order to do this, we would have to be able to compare, say, I don't know, the output of k-means clustering with different number of clusters, right? So what is a better choice? Say 3 clusters or 4 clusters, right? So it means that we should split our data into 3 clusters. We should split it into 4 clusters, and that there should be some kind of a metric, some kind of a method to measure whether it's better to go with 3 clusters or with 4 clusters, right? And if we had such a metric that allows us to compare clusterings with different number of clusters, then we would be able to do something like this. So we could remove one part of our data, construct our clusters on the remaining data set, so obtain the centroids and use these centroids to generate clusters on the part of the data that was held out to validate it. And we could do something like cross-validation, and then we could compare different choices of k. So this probably could be done in principle, but I don't really want to focus on it because there is a different method of clustering that is free of this problem. So it's called hierarchical clustering. So, and again, for k-means clustering, the choice of k, so there do exist systematic approaches, but in practice, very often we just do some trial and error. So in hierarchical clustering, we do it differently. So the algorithm is some kind of like magically constructs cluster there is no choice of k. So it will output clusters in a way so that we will immediately see 1 cluster, 2 clusters, 3 clusters, 4 clusters, and so on up to k clusters at the same time. That's the beauty of it. So here is how it works. I mean, so the idea is that we really want, so this is the problem. So with k-means clustering, right? So it's not clear how to choose k, right? So in these 2 pictures, you see a decomposition of US arrests into 4 clusters and into 2 clusters. And it's not really clear which one is better, right? So in k-means clustering, we do it differently. So here is this is hierarchical clustering. So this is how it works. So the output of hierarchical clustering is a so-called dendrogram. It tells us how these points are grouped together depending on a certain parameter called dissimilarity measure that I'm going to explain a bit later. But the idea is that if we want to use 2 clusters, right? So for 2 clusters, we look at the kind of vertical cross section of this dendrogram so that it intersects with this dendrogram twice, right? And then this is going to be cluster 1, this is going to be cluster 2, and we are just going to look at all the data points that eventually are connected to this cluster 1. And this is going to be our cluster 1. And this will be our cluster 2. Okay, but now what if we want to have 4 clusters instead? So for 4 clusters, we should do a cross section of our dendrogram here, right? And then we are going to have 4 clusters, 1, 2, 3, 4. Right, so 1 is going to be here, 2 is going to be here, 3 is Nevada until Texas, and cluster 4 is South California till Alabama. So these are the 4 clusters. Okay, now what if we wanted to have 3 clusters? For 3 clusters, we could split our data here, but the problem is that there is quite a large value. There is quite a large interval along which we would get 2 clusters. There is a large interval So it's probably from here until here. So that there is a large interval that allows us to get 4 clusters. Right? So we would get 4 clusters here and 2 clusters here. But there is a small interval in this dissimilarity that will yield 3 clusters. So which means that 3 clusters is probably not a very good choice. It's not a very reasonable choice of the number of clusters. Right? So from this dendrogram, we see that 2 is a good choice and 4 is a good choice, but 3 is not really a good choice of the number of clusters. Now, how does it work? So hierarchical clustering produces nested clusters, right? So it means that if we have, say, I don't know, say 3 clusters, then in order to get 4 clusters out of 3 clusters, we are going to split one of these into 2 new clusters. This is the meaning of the word nested clusters, right? So more generally, to get k plus 1 clusters out of k clusters, we just split one of this k into 2 smaller clusters. Sometimes this construction may not be consistent with real properties of data, and this is the disadvantage of hierarchical clustering. So you can think of, I don't know, like people in Singapore. Well, the flag is Malaysian. It's just that I downloaded this picture of the internet, so they have Malaysian flags. But in Singapore, it would be the same, right? So imagine that we have some market study, right? And we survey a pool of potential customers. And if we group them according to their preferences or whatever, then maybe there could be some kind of natural way to cluster them into 2 clusters. And it turns out to be women and men, right? So this is like two clusters. But if we wanted to go deeper and if we wanted to get 3 clusters, then instead 3 clusters would be like Chinese, Malay, and Indian, right? So like this, and this. So this is an example of when 3 clusters cannot be, well, 2 and 3 clusters, they do not form a nested construction, right? So 3 clusters are not obtained from 2 clusters by splitting one of the 2 clusters into 3. So we would not be able to detect this with hierarchical clustering. But with k-means clustering, we still would be able to detect. Right? So this is kind of a disadvantage of hierarchical clustering. Now, in order to construct these hierarchical clusters, we need to pick 2 things. So the first is dissimilarity measure between data points, and the second is dissimilarity measure between 2 groups of data points, right? So 2 data points. How dissimilar are they? 2 groups of data points, 1 and 2. So how dissimilar are they exactly? So, and the algorithm goes like this. So we begin with assigning each data point its own cluster. Maybe let me explain it on a 1-dimensional data set. So suppose that my P is 1, for simplicity, and these are my data points. 1, 2, 3, 4, 5, something like this, right? So I'm going to begin with assigning each data point its own cluster, right? And then I'm going to see which of these 2 data points are most similar to each other. And let's say it's these data points. So then I'm going to combine them into 1 cluster. And then now I have 4 clusters, this, and this. And then I'm going to compute dissimilarity between all these clusters. And those, the 2 clusters with the smallest dissimilarity, I'm going to merge them into 1 cluster, right? So let's say that, for the sake of the example, let's say that these 2 are going to be merged. So now I have 3 clusters, right? So, and again, so the first of them still has just 1 data point. And then I'm going to see how dissimilar every pair of these clusters is. And then let's say, and then I'm going to merge the pair of clusters that is least dissimilar. And it's probably this one. And then in the last step, I'm going to merge the remaining 2 clusters until I only get 1 cluster. Right? So we find most similar data points and fuse them into a cluster. And then we find 2 most similar ones and fuse them, and so on, right? And we are going to keep doing it until we are left with just 1 cluster containing all the data. So, and the dendrogram shows the values of dissimilarity at which cluster fusion happens, right? So which means that, if we have a large interval of these dissimilarities at which no fusion happens, it means that it would be natural to pick the number of clusters according to this interval, right? Now, how do we measure dissimilarity between individual points? And apart from what we saw before, this Gaussian norm in TSNE algorithm, well, we don't usually do it for hierarchical clustering. So instead, we do something simple. So probably a Euclidean distance or maximum distance or Manhattan distance. So these three are similar. So it's just that Euclidean distance is the direct distance. So maximum distance is the maximum of these two intervals. And Manhattan distance is the sum of these two intervals. And correlation distance is very, very similar. It is a very, very different method to measure dissimilarity between individual points. Now, let me explain why correlation distance is different and why sometimes it is good to measure dissimilarity via correlation rather than via Euclidean or Manhattan distance, right? So imagine that we look at customer profiles and we have 10 products and we have 3 customers and we know for each of the 3 customers which products they bought. So notice that customer A here and customer C, they bought similar products. Only customer C bought these products in larger quantities. But customer B bought kind of a different basket, but in small quantities. So both A and B bought small quantities of products, and C bought much larger quantities of products. But A and C are similar so A and B are similar in that they bought small amount of products, but A and C are similar in which products they chose to buy, right? And this is Euclidean distances between A, B, and C. These are Manhattan distances between A, B, and C, and these are correlation distances between A, B, and C, right? And notice that if you look at the Euclidean distances, then the customers that are close to similar to each other will be A and B. So the smallest distance is between A and B. If you look at Manhattan distance, then the distances themselves are going to be different, but it is still A and B that are near each other. So C is very different from both A and B in the sense of Euclidean distance and Manhattan distance. But if you look at correlation distance, then A and C are more similar and B is different from A and C, right? And for market analysis, probably we do not really care about how much stuff our customers buy, but we probably more care about which basket, so which products that they buy. And we want to segment our customers into, well, according to the type of a market basket that they buy. And in that case, we should choose correlation as our dissimilarity measure rather than Euclidean or Manhattan distance. Okay, and now dissimilarity measure between groups of points is called a linkage, right? And the common types of linkages are complete linkage, single linkage, average linkage, and centroid linkage. Now, we're going to see that single linkage is not really a good choice. I mean, theoretically it is here, but it's not really a good choice. Complete linkage and average linkage are almost the same. I mean, they do produce very similar dendrograms in the end. And centroid linkage, we are going to see in tutorial that centroid linkage is special in the sense that a centroid linkage is often useful and it is used in practice, But the problem is that the centroid linkage does not produce nice dendrograms that are nicely ordered according to dissimilarity measure. So for centroid linkage, it is possible that when we fuse two clusters, then dissimilarity measure goes down. So for complete linkage and for average linkage, dissimilarity measure always goes up, which enables us to plot nice dendrograms. But for centroid linkage, it's really trickier. So, and we are going to look at it in tutorial one more time. But this is what it looks like for complete linkage, average linkage, and single linkage. So this is the right plot is single linkage, and of course it's not a good way to cluster our observations because if you choose two clusters, then one of the clusters contains just one observation, and the other cluster contains the rest of observations, so which doesn't really help much, right? So single linkage is not really a good way to do it usually. I mean, you can try, but usually it's not really a good way. But complete linkage and average linkage, they produce very similar results, but not exactly the same, right? So like for complete linkage, the natural choice of clusters is 4, but for a single linkage, it's 5 instead. Sorry, for average linkage, it's 5 instead. So, and again, it's not probably very clear which method to choose. You can again experiment with different methods and see whatever makes more sense. Okay, so this is the end of material in this lecture. So I hope it was useful. So please do the quiz and then watch a short recap of what we learned today.